Hi, I will try the next session about the ALF's hopping routines. Okay. So now we are ready. And yeah, here Florian Goth will tell you about the hopping.
Okay. Hope you all can hear me. If not, denote in the chat that the audio quality is bad. So I'd like to welcome you to my presentation on the hoppings in ALF. And let's see, what do we have on the menu for today? So first we will have a bit of a look at the hopping Hamiltonian. Afterwards, we will look at a little bit onto the checkerboard decomposition that you might have already heard about. Then I will go with you through a simple example where we how to implement a lattice by hand. And then we will move forward to that. You actually, most of the time, if you are not really interested in that, you don't have to do that. There are numerous predefined hopping matrices available within ALF, and that it actually might make more sense for you to use that. And that will also show you which kinds of interactions, interactions is wrong, which types of effects you can include in the hopping matrix. Okay, let's see. So for you already have seen by now numerous times the general Hamiltonian of that ALF is implementing, where you have an hopping part, an interaction part, a new interaction part, an Ising part, and also a bosonic part. We will concentrate here on the hopping part, this particular structure, a quadratic form in the fermionic operators. And we assume that it can be separated into MT, number of different families, for example. Number of different checkerboard families would be an example of different hopping matrices. Let's see into a bit more detail what you have over here. So you have the hopping Hamiltonian. In here you have the hopping matrix. It is a symmetric matrix of dimensionality n dim by n dim, or Hermitian complex matrix. N dim is the spatial volume. You have the number of flavors and the number of colors, and also the number either of different hopping terms that either are given to you by the model, that you have a model that requires different hopping terms, or due to you are utilizing the checkerboard approximation for evaluating the matrix exponential. Because at the end of the day, this is what we need to find, efficient operation, an efficient method to evaluate matrix exponentials of this hopping Hamiltonian. And this is where the checkerboard decomposition can come in to speed up this part of the code. So I will spend 1 or 2 slides explaining you a little bit about that on a very surface level. And yeah, this is what we're going to do next. So we know, so the checkerboard decomposition can be, in my opinion at least, most easily understood on a one-dimensional chain example. So the task that we are trying to do is we are given the a single hopping matrix T, and we need to find a decomposition of this matrix such that the decomposition into subparts Ti, such that for each subpart Ti, I can evaluate the matrix exponential efficiently, whatever that means for the time being. And one particular example for being able to evaluate efficiently the exponential of a decomposed matrix is the checkerboard decomposition. For the checkerboard decomposition, you utilize that you can split for here in the example of a one-dimensional chain. You have next nearest neighbor hopping. So that's why on the without a chemical potential, you have no entries on the main diagonal of the hopping matrix, and only entries on the first upper diagonal and the first lower diagonal. And this you decompose into 2 parts, 2 families, 2 colors, depending on your language, where now each part in here is not commuting anymore with is commuting with each other part within this particular matrix. So only hopping on adjacent bonds is now permitted. So this is on the Hamiltonian level for a matrix. This additive decomposition would be an identity. You can split up the Hamiltonian like that. For evaluating the exponentials, you now utilize again the Lee-Trotter formula to approximate the exponential. And then you split it up into the product of the exponentiated decomposed matrices. And now the interesting effect that comes in is that with this particular splitting, where the hopping is only taking part within a particular bond, you can actually evaluate the matrix exponential exactly. It's only the exponential of 2 by 2 matrices. And the nice thing the next nice thing is also that you do not change the sparsity pattern of the matrix. With this particular decomposition, those entries that had numbers on before in your matrix also have numbers in there in the exponentiated part. Minus maybe on the diagonal, as similar over here, since the diagonal has been 0. So you still have this nice feature that your Hamiltonian only contains a linear amount of information. The exponentiated part also contains only a linear amount of non-zero entries. And this is the basic idea of the checkerboard decomposition. You can generalize this to you can generalize it to the arbitrary matrices. What is implemented in ALF are already maybe the most common lattices. So of course there is an implementation for 2D square lattices where you now have 4 different families of checkerboard. So the Hamiltonian has been decomposed into 4 subparts. You also have the honeycomb lattice. There it's 3 families, and there all of these things have already been worked out for you. You don't need to implement these kinds of these decompositions for yourself. And yeah, let's see. Let's move on. So let's assume you want to implement a hopping for yourself. So let's do the simplest part first, considering the hopping matrix in a certain way only as this thing as an adjacency matrix, which encodes hopping between the sites that you want to connect with each other. We do not include any other effects so far. This is for later. And let's assume we do this for the simplest example we know. So the Hubbard model on a 2D lattice. So this is this particular lattice over here. And the matrix structure that would correspond to this would be something like this. So this would be non-periodic boundary conditions, it seems, what I've plotted over here. ALF most of the time uses periodic boundary conditions. And then what you need to write is a Hamiltonian, which extends the basic Hamiltonian and defines a certain number of variables that the code needs to run. Some of these variables are already provided to you by the base class, so these operator things. So for example, the interaction operators and also the hopping operators. Also the basic Hamiltonian variables, so the size of the matrices, the number of flavors, number of colors. But for example, the lattice dimensionalities or the chemical potential, these are things that you need to have in your Hamiltonian yourself, that you need to write there. And you also need to write code that reads in these parameters from files. You have seen this operator, so I'm reiterating a bit what this operator is going to look like. The operator is a basic structure which is utilized for encoding the information in the interaction vertices, but is also utilized for encoding the information in the hopping matrices. So you have O matrix itself, which you have this projector matrix that allows you to express bigger sparse matrices into smaller matrices where the columns and rows are brought into blocks closer to each other. You have the coupling strength. So in the case of the hopping matrices, this is delta tau times t. And yeah, so the constant alpha, which is not used for the hopping, but in the interaction term. And these are the parts we have to set, the variables that we have to set into each operator, because we are going to create one of these operators ourselves in this particular example. Later on, I will show you how you work around this work. Okay, so how do we do that? So we usually in all the Hamiltonians follow the convention. We have a subroutine ham hop, which, as the name implies, sets the hopping matrix, and it follows a kind of loop. So first we have to create the hopping operators. For this you utilize the op make function. And then, assuming you have set up a lattice before, it's a separate function, hamlet most of the time, then you set the entries of this matrix. So this is a loop going over the matrix and putting a 1 or a delta tau times t in all those places where you want one, or you leave it at 0 if you don't want to have a connection over there. What else? So of course, for the Hubbard Hamiltonian, you also might include a chemical potential. And at the end, you can, if you have set up the Hamiltonian, you can call this op-set function to basically such that you tell the operator, okay, now I've given you all the information that you need. Initialize all your internal data structures that you need to work properly. And then, if you have written your Hamiltonian somewhere in a Hamiltonian set function, you will call the hopping Hamiltonian. This is what you would need to do if you write this hopping matrix yourself. So you have to write the information for the matrix somewhere. That's the idea behind that. But most of the time you don't need to do that. And actually, there's a there's code available that allows you to do even more general things than just setting the connections between matrices. Because the ALF collaboration has invested a lot of work into figuring out what the most generic hopping could look like. And since you can also include magnetic fields into the hopping, you can include effects of the boundary conditions into the hopping. And making the complexity of the Hamiltonian structure far more complex than just the adjacency matrix, basically, that you have here encoded into the T matrix. If you need this flexibility, you can utilize where is it, the generic hopping function that you find in the documentation, and this will give you a data structure, a hopping matrix data structure, which with the respective information. But around this generic function, there are wrappers already built for specific lattices. So, for example, the very common thing, hopping on a square lattice with magnetic field and fluxes in the lattice. So this would be if you have this kind of Hamiltonian with a vector potential on a square lattice, then there is a wrapper function that you can call set default hopping parameter square, which basically gives you a hopping matrix object which encodes everything that you need to create the hopping operators from the information. So the T vector chemical potentials, the 5 fluxes in different directions, and also the lattice. Also available is the same thing for the honeycomb lattice, which that you can include. And also the other very common lattices that we have available are the bilayer structures that you can set up. So you can have bilayer structures of square lattices, or you can have bilayer structures of honeycomb lattices on top of each other. And also the n-leg ladder systems are, there's also a default hopping parameters, n-leg ladder, something is also available. Okay. So what would, if in this setting, if you try to use the predefined structures, what would your workflow most of the time look like? So first you have to set up a lattice structure somewhere. So there's a lattice library for creating that. This gives you the, where is it? The list, inf list, let unit items over here. And also then you call set default hopping for the particular predefined hopping that you want to use. This returns a hopping matrix type object, which encodes all the information that you have given to it. And after that, you can there's a separate wrapper function, this predefined hopping set opt, which takes the information that is stored in the hopping matrix type object and creates the opt objects that in the simple example for the Hubbard model, we have created that ourselves. We have set every matrix in the entry. If you use these predefined hopping types, you don't need to do that yourself. These are set up by the predefined hoppings set function. And so in Fortran, what would it look like? So somewhere you have an allocatable object for the hopping matrix array, multiple of them, and also yeah, so one particular, you can also, the checkerboard decomposition is handled by the set default hopping functions. You tell it if you want a checkerboard decomposition, and then it will create the respective objects. And then you call set default hopping parameters with this argument. This sets up the hopping matrix object, and then you can call predefined hopping set opt to set the opt vector that is available in the Hamilton base module. Okay. And so with that, I would be at the end of the session. So what has not been covered over here is this flexibility of using icing fields. So there's a separate chapter that you find in the documentation detailing a lot of work of the that people have been doing on Z2 gauge theories. And I didn't go into too much detail here in the internal structure of the hopping matrix type, since it's basically hidden away from you as end users by the wrapper functions around it. And so with that, I would like to thank you for your attention.
Thank you, Florian, for introducing the hopping. Are there any questions? Sorry.
In the page that determines the hopping matrix, I noticed that somehow the lattice structure is hard-coded into that part. Is there a possible way for the user to have more freedom in choosing the lattice type? Because I noticed that the code is basically doing a convolution with a certain lattice kernel and the lattice itself, and it produces the hopping matrix. So I wonder, is there a plan to implement a way that allows more flexible selection of the lattice by using a kind of approach?
So if you are talking about plans, maybe Farker is better suited to answer that, whether you want to have something more flexible. In my opinion, you have full flexibility in that sense that you are free to specify the hopping matrix whatever you want. I mean, I get it. It's a very handwriting approach, all the entries. I wonder what kind of intents you had for other lattices. Do you need more 2D lattices? Do you need more 3D lattices?
I'm scared. You have too many bottles.
Yeah, I mean, currently you would need to specify the rules of which element is which inside the for loop, and I think there's actually a better way that you provide with a certain smaller matrix that determines how each lattice point do the hopping, which, yeah. Yeah.
You avoid these, it's okay.
Yeah.
So can you go back to you had a slide where we were looking at the hopping? No, this one, yeah. This is the minimal, this is basically the structure we have, right? And so it's pretty much independent on the lattice, right? No?
Yeah, but I think he wants to specify less information for specifying T. Currently,
There's no less, I came to the conclusion that the way we do it, we put so there is you put the k equals 0, right? For example, when you want to do that, you have translation. So k is a unit cell and delta is an orbital in the unit cell, correct?
Yeah.
Right? And then you have so you put k equals 0, okay? And then you have just relative distances. Okay?
Yeah.
And then that is, let me just finish what maybe to be sure that we're on the same page. And so the T which you provide here is the minimal information you need to provide the hopping for a given provided you have translation symmetry. That's my claim.
I think the feature that you are looking for is actually already to some extent encoded in the hopping matrix type, the type that you didn't explain, since this is like only the internal structure. But maybe Farkia can correct me if I'm wrong. The hopping type essentially encodes, if you're on a specific site, which site do you connect to? And this is the information that you use combined with translation symmetry to connect every site to the appropriate neighbors that they are connected to.
Yeah, I wonder.
I think, yeah, I think we're not understanding.
Yeah, I would like to say, is it going to be better if the user can directly provide this entry, the like hopping matrix type, into the function, so that it's going to be easier to modify?
So you would like a function where you provide the lattice and the T.
Yeah.
The local T with, so let me put k equals 0, right?
Yeah.
Right. And so that's, you have j minus k then, right? And that's what you provide. And you set up the lattice based on that so that you can easily modify your hopping without going into deep in the code.
Yes.
That's what you want. That's no problem. No, that is a problem. So that is it. Okay, so here's the thing. If you want to do a checkerboard, right? The checkerboard, we don't. So Florian has somewhere. Okay, let me go 2 steps. If you have an arbitrary range hopping and you want to generically generate the checkerboard, then that's a bit of a pain.
For general graphs, you can't even have. It's not a.
Yeah, but you can find some type of decomposition. You can. Florian has an algorithm to do that, so he can do that. The question is it the optimal one or not? I think that was an issue.
What is optimal?
Huh?
What is optimal?
Optimal is not so many matrix multiplications, right? So optimal
This is an NP hard problem of finding that.
Yeah. Okay. So it's a.
But so the code that I have available, either it's optimal or it's one family away from optimality. These 2 options it has.
So that's what you want, right? I mean, so we have to combine we could define your function and then combine it with based on the T, we build up the graph, and then we have an automatic way of doing the Trotter decomposition. That's it. Because when you do the Trotter decomposition for the square lattice, it's going to be different if I have a T checkerboard. I'm sorry. I said Trotter, I understand. If you do the checkerboard decomposition, it will be dependent on your if you have a T, T1, T2, T3.
Yeah, I'm aware that not all lattices can be decomposed in the same way.
Yeah, but but that means you want a intelligent code that does this for you. That's what you're asking. I think it's a good thing to ask.
The basic idea for those who are interested, you kind of see it over here. That if you have a graph, that's what it basically is. The checkerboard decomposition corresponds to a color decomposition of the matrix. That's such that each bond has a different color. And there are algorithms for doing that to graphs. And yeah, lattice is a graph, therefore it exists.
But then when you have this, and you could, if I have this, if Florian, you have it, right?
Yeah.
So if we could implement this somehow, we could do a function that, given a graph, returns the one possible checkerboard decomposition. Then
It's not a unique decomposition.
it's not unique, right? It's not unique. So just one. Then you could have an arbitrary. Then you could have a very that would be very useful actually.
I guess the idea.
Bye. Careful.
So I guess the idea is, let's say we want to modify the square lattice, and you want to modify it in the way that you want to add second nearest neighbor hopping terms. That there is an easy way of specifying the bonds that you want to add, like the second nearest neighbor or third nearest neighbor or whatever hopping terms you want to add, without going through all the.
So that won't work, right? For the moment, that will be a lot of work. If you want to add a T prime or something like that, you have to go down into the code, down into one thing which you don't want to look at, and you'll build in a bug and you won't make, I mean, it will be painful.
Yes.
I agree.
Yeah.
It's very, I agree.
Wonderful.
No, that's not true.
There are some of the things like that.
Yeah.
Yeah, so the idea is to find the easy way to specify the hopping, whatever it is, like nearest neighbor or second nearest or third nearest, and then produce a graph of lattice based on this kind of small matrix, and then use the graph to perform the checkerboard decomposition and do everything. Yeah.
Another possibility which we haven't really used is the fast Fourier transformation. That is not so much slower than a trotter, right?
Technically, yes, since you have a logarithmic term, which you usually don't notice.
Yeah, so you don't notice the log term, so it's the log. There's a log difference, and then maybe for your thing, an easy way around is to say, okay, forget about the checkerboard decomposition, just do fast Fourier transformation. That would be an easy way, and that's really general. That's basically generic, and you don't have all these nitty gritty issues of that. That may be a good thing to think about. And then you'll solve your problem.
Which direction you want to go. This particular structure is let's move it over here. This is kind of, so you're thinking more in the terms of a model building approach. I know the local interactions where I have other ideas. If you come, for example, from a DFT calculation or so, which is an idea that occasionally was floating around, which directly gives you the matrix with all its entries and some which to you look mostly like random numbers that you can directly read in from files when it's just file IO.
Okay, so if there is no other question,
Chat, I don't know.
I think so. Is there some question in the online audience?
No.
So then let's continue with our next part, which